Okay, morning. Just a quick demo. I think I forgot to show you in the previous lecture. When we started previous lecture, and I mentioned about there are basically two different kind of stress or two different critical locations when a gear are moving, pushing each other. We said basically there's a location where they get a contact, and there's a location, the root location. So this is a simulation using ANSYS. You can see clearly the stress, right? The user one means stress. One is the contact, the other is the root location, right? Yeah, it's moving. Okay, yeah. So we'll continue on this gear design here, okay, to come up with the preliminary equations for gear design, and then we'll go into this AGMA equation. I think it probably will be the next lecture now. Okay, so this is the diagram I showed you in the previous lecture. We're talking about the Lewis equation, okay, for tooth bending stress. Okay. To quickly recap what we did is, so Lewis in 1892 find that he can use a constant strength parabola inscribed inside this gear tooth profile to represent as approximation of the gear tooth, actually as a conservative estimation, approximation. Okay, conservative meaning anywhere outside this constant strength parabola, like this location, they have less bending stress than those on the parabola. Okay, yeah. So what we did is basically we're trying to derive what is the bending normal stress at the root location, because as you can see, the nature of this construction of the constant strength parabola is it's tangent to the root location. So anywhere along the tooth profile is smaller, has a bit smaller normal stress, but except what? Except the root location, right? So we just need to get this is the critical location. What is the bending normal stress at the root location? Okay. So here's some dimensions that are here, L and T. Okay, like this. So in the first lecture, I think what we derived is the sigma equal to WT over F times Y times a small p. Okay, small p is the circular pitch. And small y is 2x over 3p. Okay, 3p. X is this geometry. Okay, is this geometry. If we draw a symmetric lines right over here, okay, passing through this top center point here, and then we can draw a perpendicular line to this tangent line here, and the quantity x is this much. Okay, this much. Okay, yeah. Small y here is called Lewis form factor. Okay, Lewis form factor. Okay, now, but this is not the final. Okay, Lewis form factor. More commonly used one is we go from here one more step. Instead of using circular pitch, small p, we would like to use the diametral pitch, the capital P. Okay, yeah. We know that the diametral pitch, capital P, is related to the circular pitch, small p. Okay, using pi over the circular pitch, you'll get the diametral pitch. Okay, yeah. So what we can do is basically we can do a very simple substitution here. We can let a capital Y equal to this pi times the small y. Okay, yeah. So small y is a Lewis form factor. Now if we change the small y to capital Y, we still call it Lewis form factor. Okay, yeah. So this guy here is also Lewis form factor. And this is what we're actually going to see in most of the tables. But the sigma, okay, which is originally this one in terms of the small p and a small y, and they will be changed consequently. Very straightforward change by substituting all the symbols. Okay, you'll get this sigma become Wt times capital P. Okay, this is capital P over F times capital Y. Okay, capital Y. And capital Y now is pi times Y is actually 2 small x capital P over 3. Okay, so this is basically Lewis equation. Lewis equation for tooth bending stress. Okay, tooth bending stress. You need to be careful here. The F is not the force, huh? The F is the phase width. Okay, and Wt is the tangential force or the transmitted load. Okay, it's not W, huh? It's not W. Is that okay? Yeah. Okay, so now from here, let's do a few observations first. Okay, and then we'll make a few conclusions. But first of all, okay, let's realize the limitations this Lewis equation has. Okay, the limitations, or essentially, what are the assumptions that Lewis has made. Okay, so let me still call it limitations or assumptions. Doesn't matter. Okay, some of them are very obvious. Okay, now see, first of all, you look at this one here. We're talking about the bending normal stress at this location here, right? If you're going to do bending normal stress, okay, if you have a bar, okay, attached to the wall, okay, yeah. So if I do a similar analogy like this guy here, I have a force going down. I have a force going this way. This is Wt, this is Wr, right? This is Wr. And guess what? The Wt will generate the bending normal stress, right? What does Wr generate? Compressive stress, right? What direction is the bending normal stress? On the about cutting cross section. Where does it point to? This way. And where does the compressive pointing to? That way, right? So if you're really looking for bending normal stress on a cross section, theoretically, what do you need to do? You need to use the bending normal stress from this one, and then what? Subtract this guy here, right? But the Lewis equation, you look at this one here, it didn't consider this Wr. It actually neglected Wr. Would that be a good or would that be a bad actually? Would that make it more conservative or make it less conservative? By not considering Wr. Or then let's put it this way, would that make the bending normal stress bigger or smaller by neglecting Wr? Bigger. You're using a bigger stress, which means you have a conservative or less conservative? Conservative, right? Yeah. So that's one thing in here. Okay. First assumption or limitation, which is actually not too bad, right? So Wr is neglected. Okay, but it make it a more conservative model, right? Okay, it's more conservative, which is not bad because as a design, you want it to be conservative a lot of time. Okay, yeah. And second of all, the Lewis equation does not consider stress concentration at the root fillet location. Okay, yeah. So that's another limitation. As a matter of fact, because he discovered this, he discovered this formula, okay, in 1892. And guess what? In 1892, actually nobody knows stress concentration yet. Okay, yeah. Okay, so that's second limitation. But that's truly a limitation, which is actually why later for AGME equation we're going to have to compensate this limitation. Okay, yeah. And the other thing is what Louis says. He considered the force concentrated at the tape. Not exactly the tape, actually. More precisely, the tape should be here, right? Yeah. But there is, because of instruction here, there will be a slight difference, but it's negligible. So he's considering the force at a tape. But if you remember the video I just showed you there, when the gears are engaging each other, then the W, right, is the force perpendicular to that surface of the engagement. So the gear not necessarily is always what? A tape to tape, right? Yeah. And a lot of in time you have this contact right here. So maybe the contact is right at this location. That makes sense, right? Yeah. However, the way we calculate the Louis equation, we consider basically the most extreme case at the tape, right? That's actually not a bad thing, okay? Yeah. So that's in the second. That's another one here, okay? So force is concentrated at the tip. Okay? Yeah. And there's one more. Friction is neglected. Okay? So when the two surfaces are pushing each other, okay, there's not just rolling, but maybe there's also what? Sliding. Okay? Yeah. So that basically will create friction. But the friction is not considered. Okay? So you see, there are basically this many of assumptions. So yeah, there's one more assumption is it's assumed that the force is evenly distributed along this face width. Okay, that's the last assumption. Okay, yeah, which is a reasonable assumption. Okay, so I'm going to write it here. But anyway, those are limitations. So you see the limitations, then the idea is we want to accommodate those limitations, right? Yeah. So we'll see how we accommodate those limitations. But let's go back to this equation first, okay, to the Louis equation. Okay, Louis equation. Bear in mind the Louis equation gives you the bending normal stress at the root location. So you look at the sigma. What does sigma depends on? Sigma always depends on WT. Sigma also depends on what? On the Y value, right? Sigma also depends on the Y value. As the Y changes, the sigma will change. So basically, it's a form factor. Why is it called a form factor? Because Y apparently depends on which parameter? Depends on the X, right? Depends on its X. X is this much here. So when you design a gear, you often pick a number of teeth, and you pick a diametral pitch, right? So the gear tooth profile has a form. As you change the number of teeth or the diametral pitch, so the gear tooth, the profile will slightly change, right? And that change, guess what? Will result in the change of this X. That makes sense, right? So, say for example, right? I'll show you using my software to my drawing will not be bad and will not be good, but to illustrate, let's say you have a pretty narrow body here. Okay, a pretty narrow. Okay, pretty narrow body at here. Then, what's the X? This is X, right? This is X. So if the tooth becomes, instead of a narrow, you become a bit of a puffy one now. Okay? So guess what? The tangent line, you still draw the tangent line here, right? Because the X depends on this tangent lines to the root location. Huh? Yeah. So you still draw the tangent line, but the tangent starting from the same peak point. So the tangent line will become this now, right? So the tangent line, this is the first one, the second one is this. So imagine what happens to the X. The X will actually what? Increase or decrease? Increase, right? That's why it's called a form factor. So it changes with the geometry. It's a form factor. Okay? Yeah. So let me show you this this one here, and then you tell me how does the form changes. Okay? Yeah. Look at watch for people from behind. You might want to stand up to watch here. Okay. So the bottom one is the pinion. Okay. So I'm gonna just watch this bottom one here. Okay. Watch this bottom, this purple one here. Okay. Watch the purple one. And right now the pinion number is 18. Diametral pitch is 20. Right? Yeah. So this is the shape. Okay. So what do? You basically can draw a tangent line up to this location, right? And you can find x by drawing perpendicular, right? Okay. Yeah. So then what happens if I increase the pinion number? Okay. Watch the tooth form. Look at the bottom there, huh? And then what happened? It's thicker, right? Yeah. Or in other words, actually, the tooth profile becomes more like a straight line, right? More like straight line. So now you tell me, when I increase the pinion number or the tooth number, the x supposed to increase, right? Increase. If x is going to increase, okay, so this is the first, I'm writing it here. So p constant and n increase resulted in the x increase. X increase will result in the what? What does result in the capital Y to increase. So that Lewis form factor will increase. Y will increase, will result in the sigma to decrease. Okay, to decrease. So simply put it, the higher number you have, the less bending normal stress at the root, right? That's basically the idea. Okay. Yeah. So now in later you design a gearbox. You have a pinion engaged with the gear. So you will calculate the bending normal stress for both the pinion teeth and the gear teeth, huh? Yeah. But now you think of it, how many teeth on the pinion, how many teeth on the gear? And chances are the pinion will have less teeth than the gear, right? So the simple question is, when you do the calculation, you should always check is, what would you expect the bending normal stress on the pinion and the same one on the gear? Which one would be bigger? Pinion has smaller number of teeth. Which one would have a bigger bending normal stress on the tooth? Pinion, right? So if your calculation is the other way around, then something wrong. Okay? Yeah. Okay, so the next observation. If I'm going to keep the n constant and change p, okay? So let's see what happens, right? So this is not a mathematically rigorous proof, but I can really show you the proof, but I think this is enough here. So I can change diametral pitch here, okay? You observe the tooth form, okay? Tell me if there's any change at all. So I'm going to change to this now. Anything changed? So let's change another one here. So no change at all, right? Well, but you observe, let's observe this guy here, okay? Observe this, let's use a pinion active here. Observe the base diameter, huh? If I change the diametral pitch, those parameters, those of the gear parameters, they changes, right? They change. Okay? So it basically means, when you change the diametral pitch, keep the number of teeth, the size of the gear will change, huh? But what's not change? The form, right? The gear profile, the tooth form, it doesn't change. Okay? Yeah. If the tooth form doesn't change, does the Y change? The Lewis form factor. The Y, as we observed, it doesn't change. Okay? It doesn't change. Alright? Yeah. That's a simple observation, right? Yeah. Basically, the form doesn't change. Actually, it's quite easy to understand. If you remember, we have the two parameters. One is called addendum, the other is called what? Dedendum, right? And addendum value is what was it? I think it's 1 over p, and this is 1.5 over p, something like that. Okay, so if I correctly, okay. So if the p doesn't change, so actually the addendum and dedendum, they don't change, right? Yeah, they don't change. Okay. Yeah. Okay, so here's another diagram, shows you the change of number t's in terms of the Lewis form factor in terms of number change, and also there are different pressure angles. Okay, so there is this 14-degree pressure angle, 20-degree pressure angle, and then there is this different tooths. They call it stub tooth, not a full tooth, right? Yeah. So as you can clearly see, as I written over there, so the y, the Lewis form factor, depends on a couple of factors, couple of reasons, right? One depends on the number of teeth. The other depends on what? The pressure angle. The higher pressure angle, the what? The higher Lewis form factor. Okay? Yeah. So you keep those things in mind. Sometimes it can give you roughly a sense of where you're going, right? Some of these common things. And this form is from our table 14-2. This is basically a pre-calculated Lewis form factor. You will need those numbers. Given the number t's, you need the corresponding number for our future calculation. Okay, so this is one table you will resort to quite often, huh? Yeah. Okay, so having said this, now let's consider a couple of things to modify this Lewis form factor. Okay, yeah, because this is not going to be the final form you will use for design. This is just the starting point. Okay, the very beginning things that we can do to modify the Lewis form factor is this. So this is Wt times P over Fy. Okay, for Fy. So let's say modification. Okay, number 1. So we have many to come, huh? But today let's just focus on only one here, maybe, huh? Yeah. The number 1 modification is this. When gears are in contact with each other, okay, the fundamental objective for a gear to engage each other is what? To ensure a constant velocity ratio. Okay? Yeah. But the question is, you don't get to maintain that often, actually. Often in time, when you have a gearbox, when you drive a car, you hear some clunking noise, right? Yeah. So what caused that? Basically, and when that happens, you don't really have a constant velocity ratio at that stage. Okay, and that's different reasons. One of the reasons may be there's imbalance of the gear. Right? After some while, it's wobbling, or maybe there's because of wear of the tooth. Okay, and then there's some frictions or some other defect. Okay. Or maybe because the shaft is not perfectly aligned, or the shaft is being defected, right? So all of this reason, basically, as you're rotating at a certain speed, you don't get to maintain that kind of a constant speed ratio. Okay, yeah. So what we need to do is that consequently will cause an effect on the bending stress. So what we need to do, we can modify this or basically correct this, okay, using a factor. Just like the stress, just like the endurance limit correction factor. So we correct that first one. We can use a simple so-called dynamic factor, Kv. Okay, so Kv is called dynamic effect factor. Okay, yeah. So that's the early stage of modifications that did to the Lewis equation. Apply a dynamic KV. So KV, often in time, you can find that from like AGMA catalog or code. So one of this that you will see that KV is this much. Okay. So this is equation 14-4b from the textbook. Okay. Yeah. So 1200 plus V over 1200, and V is the pitch line velocity. So you have a gear in contact each other. So at the pitch point, you have this pitch line velocity. That's the V. All right. Yeah, that's the V. Okay. But you got to be careful though, huh? This is actually probably not going to be what we're going to use in terms of actually AGMA equation. But I'm just kind of show you an example what you can do to crack this sigma, huh? To crack this sigma. Okay. As a matter of fact, as I'm going to show you later, there are many things that will be applied to the factor here. Okay. So as you can see, this is more than what we're going to see in terms of endurance limit. For the bending stress, we're going to apply at least 5 of them at here, right? Yeah. Okay. But one of them here is that's the KV that I just showed you there, right? Yeah. But the caution is, okay, don't stick to this formula. Okay, this just for example. Okay, we will have a couple of more formulas for the KV. Okay, in terms of AGMA code. So, but now you kind of get an idea of what's going to happen, right, in terms of modification, right? Yeah. Okay, so then the next question is design, right? So here's the bending normal stress now. How do we do the design, essentially, huh? Yeah. To do the design, there are 2 different ways. One is what I kept saying, the AGMA, which is what we're going to use. But there's another one is what we learned in our previous lecture. Okay, if I'm going to do the design, we can really actually also use the previous what we learned from previous lecture. So you have a gear tooth, and you have another gear tooth, and they are in contact each other. For example, right? This is W. So if you examine the variations, if you examine the variations of stress on the gear tooth, so basically they engage, contact, and disengage, right? Yeah. So you can always draw what? The stress, the bending moment on the gear tooth is like this. So increase back to 0, coming back like this, right? Yeah. So that's what the bending moment will vary on the gear tooth. Okay. There's only one difference, right? There's only one difference. Okay. This is when you have basically driving and driven. But remember, in the gear train, there's one particular gear is called idler gear. So you have basically a gear sandwiched between 2 here. So this one drives this, and then that drives the next, right? Yeah. So what happened to the teeth on the idler gear? If you have a teeth at this location, it feels this, and as the teeth goes over here, engage with this guy, it feels that, right? So for idler gear, the bending moment verification is it feels this, negative, positive, negative. Okay, that's the idler gear. But anyway, if I'm looking at this guy here, this is the bending moment, and the amplitude is basically half of this. So this is MA, and then in the middle is MM. So you can always get sigma A, you can always get sigma M, using the MA and MM, right? And MA and MM. As a matter of fact, as you can see in this case, we can consider them the same value, sigma A and sigma M. And what are the sigma? What are the value then, right? They are, let's say, this is maximum is the sigma at here, and that sigma is the Lewis bending normal stress. I use the formula there. So you can use 1/2 times the KV, then times WT over P over F times Y. Okay? So there we go. So you have a basically it's a fatigue loading. You can calculate the amplitude, you can calculate the mean stress, the mean, right? Yeah. And once you get sigma A, sigma M, fatigue loading. So I can have several different criteria: Goodman equation, Soderberg, ASME, elliptic, right? Yeah. And I guess you also need to calculate endurance limit, correct endurance limit, and calculate safety factor. That makes sense, right? Yeah. So that's one way of doing it. So check out this example 14-2 if you're interested in the details of doing in this way. All right? Yeah. However, as I said, we're not going to use this way to do it. We're going to use the more of an empirical approach, that AGMA equation that I showed you here. Okay, so we're going to use this approach. All right? Yeah. Is that clear? Okay. So I think we're up to this stage. What you need to bear in mind is we have a Lewis equation now, and that's the basis equation we're going to make use of to modify it, okay, to do our design. But that's only for the bending normal stress, right? Bending normal stress. As the video shows you, okay, you do have another stress, which is the contact stress. Okay, contact stress. So let's look at a simplified version of contact stress, and then we'll look at the AGMA equations, which is modified one based on the simplified version. All right. Yeah. So the title is basically we call it contact stress. More precisely, we're going to call it the Hertzing stress. Okay, on gear tooth. Okay, on gear tooth. Okay, so what's Hertzing stress, and how do we deal with this contact stress? Now you need to also realize this: a gear surface will tend to wear given certain amount of time. But what caused the wearing of the gear surface, right? There are a number of reasons. One is pitting. Okay, for this wearing of the gear surface. One is pitting. Pitting is basically because the repetitive high contact stress between the two surfaces. Okay, that's the pitting. The reason for pitting. Okay, so second of all is a scoring. Okay, scoring. Scoring meaning if you don't lubricate it good enough, then you will have scoring. Okay, because of heat and other things. And last one is abrasion. Okay, abrasion. And this one is due to what? There's some kind of foreign stuff stuck in the middle, right? And then that's the abrasion, right? Yeah. So in our case, we're going to focus on this pitting. That's what we're saying. Okay, the contact, the varying due to high contact stress between two surfaces. Okay, yeah, pitting. So in other words, often in time you see that the equation later, instead of calling it contact stress, Hertzing stress, you'll see it's a pitting stress. Okay, you also call it pitting stress. Okay, yeah. So here's the idea of contact stress or the pitting stress. This is the gear in contact each other. Okay, yeah. Through many evidence, okay, many evidence that the wearness, first sign of wearness, always appear on the pitch line here. Okay, on the pitch line, basically somewhere in the middle of the gear tooth, essentially. All right, yeah, that's the first sign. So then what people do is, okay, so let's look at this engagement here, and let's approximate the two gear at this pitch line location using two cylinders, right? It look like cylinder, but not really, right? Yeah. So you use two cylinders to approximate the two gear tooths, okay, two gear teeth. So cylinder is this, And they're very well developed stress, contact stress, for two cylinders in contact when you apply a force, pushing, compressing each other, right? Yeah. Now for contact stress, this is the model people derive. You have two diameters, okay? You have a force, then the kind of a contact stress at this location, basically it's not a perfectly rigid, and there will be some kind of a deformation, right, at this contact. And that contact stress at this location is this distribution. It's basically, if I amplify that a little bit more, it's this much distribution, okay? Okay, yeah. It's not a even, it's not constant. Somewhere maximum over here and here, huh? Yeah, that's right. The distance, this much distance here, 2b, is supposed to be how much material has been flattened, because the compressing, right? 2b, okay? Yeah. So without too much here, we can calculate, okay, what's the maximum basically stress or pressure, okay, which is this location here, the P max. Okay, yeah. That's one of the things that you will find in your textbook, actually, chapter number 3, if I remember correctly. Okay, but anyway, we don't really need to worry too much how is it calculated, but all we need to know is, okay, those are the values that you can easily find it out. Okay, yeah, in terms of the maximum stress. Okay, yeah. But the idea is, for the gear is, you're considering this gear as two cylinders. Then the maximum stress at this location will follow the results at here, right? Will follow this result. Okay, yeah. So how do we follow the results then, right? How do we follow the results? So all we need to do is we just need to make an energy at here. Make an energy. Okay. So if you look at the formula here, what are they? Okay. So there's F here, right? There's F. So maybe I can replace F with what? W. Right? You see, this is F here, and this is what? W, right? This is W. Okay. The pressure angle, right? Yeah. And in this formula here, there's D1, D2. And D1, D2 representing the diameter of the two cylinder. So in my case here, I think I can use what? This is the diameter of the two cylinder, right? So we can draw two cylinders or two circles tangent to each other at this location and here, right? Yeah. So we can use basically the radius, which is basically half of the diameter here, as the parameter D1 and D2 here. Make sense, right? Yeah. And to find R1 and R2, it's actually pretty simple. You can use geometry to find R1 and R2 very easily. Okay. You can find R1. So if this is the diameter of the pinion, pitch diameter. Sorry, this is the base diameter of the pinion, right? This is the base diameter. So what you're gonna end up with? Sorry, this is actually pitch diameter. Why is it pitch diameter? Okay, anyway, okay. So you find R1, okay, equal to dP times sine phi over 2, and R2 here equal to dG times sine phi over 2. So all you need to do is replace the R1 and replace the D1, D2 with R1 and R2. Okay, yeah, in this formula, right? In this formula. E1, E2, they are the Young's modular for for pinion and the gear, depends on material. V1, V2, they're the Poisson's ratio. Okay, yeah, mostly metal has the same Poisson's ratio, so you can consider as a constant at here in terms of the gear, right? Yeah. Okay. So that basically more or less wrap up the. Oh, there's L here. And L is which dimension? What was L again? All right. L is you got to look into it, right? It's a cylinder, so L is this much of contact, huh? That's L. Okay. So in this case here, what will be that? You replace the L with the face width, right? The face width. Okay. Yeah. So those are basically the replacement you can do in terms of the replacement. L with the face width, and D1, D2 with R1 and R2, right? Yeah. And I guess you can always replace E1, E2 with E pinion and E gear, okay? Okay. And V1, V2, you can replace that with V pinion and V gear, okay? Poisson's ratio, okay? That's it. Then we'll end up with our contact stress at here, okay? And it was the contact stress. So if I write it down at here, yeah, well, I don't want to write it down here. Maybe I'll just copy here. It's a pretty long equation at here, actually. There we go. So I'll write it down, put it down here. Okay, so this is basically the end results of the contact stress. Sigma C is the contact stress, or Hertzing stress, or pitting stress. Okay, this is preliminary, not the final results we're going to use. Yeah. I do plug in the kV. You actually don't need to have this here, but because later you will have a whole set of others at here. Okay. And Cp is called elastic coefficient at here. Okay. Yeah. So this is the fundamental, the basis equation for contact stress. Okay, for contact stress. Okay. Is that good? Yeah. So then you have two equations now. One is for bending, one is for contact. So finally, this is the next big things that we're going to deal with. We're going to modify the two simple equations with many other empirical correction factors. So for example, okay, you only need to focus on one because I listed two different unit formulas, right? So we only need to look at basically this one and this one here most of the time. Okay, we're dealing with the US unit here. Okay, so let's take a preliminary examination at here. Okay, yeah, you don't need to worry too much the name of each one of them. Okay, but you can definitely compare these two equation. Okay, these two equation with the simplified equation. This is a contact. This is a Lewis form. Okay, yeah. So observe one thing. For the Lewis equation, the denominator, which is what? This is y, right? But in AGM here, instead of using y, they're using a j at here. Okay, using a j. See that, right? Now remember one thing I mentioned. The y, the Lewis equation, it didn't consider the stress concentration, right? So in the AGM equation, later you'll see in the next lecture, when we calculate the j, we actually took this stress concentration into consideration. Okay, yeah. So this is what I mean by modification here. PD is the diametral pitch. Okay, so sometimes my symbol, I use the capital P in that equation, right? But here, to be consistent with the textbook, we're using PD for diametral pitch. Okay, yeah. So some other factor like KO is called a loading factor. KV is the dynamic effect factor. KS is the size factor. Okay, and the Km is called a misalignment factor, and Kb is called a rim thickness factor. Okay, yeah. So basically, you're protecting yourself with all different kind of possibilities, right? Yeah. For the contact stress, you have a similar ways of correcting them too. Basically, huh? Yeah. So KO, KV, very similar. You have also KO, KV, KM here. See, there are 4 factors can be used to both stresses. Okay, yeah. So anyway, we're going to talk about this in the next lecture. In the past, what I have been to do is, but I don't know if I can still do this year, is I've been asking you guys actually to prepare slides on those factors. Yeah, it's actually fun, to see how your understanding, how you teach. If you're supposed to explain what are the factors is. But given the short class time, so I'm actually gonna take it over and I'll probably do it here. But if you're interested, you can always take a look at it first. Okay? Yeah. Okay. So bottom line is you get 2 stresses, right? So what do we do with the 2 stresses? You're designing. So what do you do with the stresses you calculated? You need to compare the stresses with what? Strengths, right? You need to compare with the strengths. So we're going to have 2 more basically equations. One is a sigma allowable for the bending, and the other is going to be the sigma allowable for the contact stress. Okay? Yeah. So you calculate the 2 stresses, and then you calculate 2 allowable ones. You compare to each other. Then you know whether you're safe or not. Right? Yeah. The 2 allowable ones will incorporate the safety factors into it. Is that good? So that's the bigger picture, right? Yeah. Okay. So I'll start using the AGMA in the next lecture. Okay. I should be probably going pretty quick. There are so many factors there. Okay. So.